Physics is the study of the world around us, and in the world around us, many objects are stretchy and springy, such as elastic bands. We have these kind of squishy stress balls. We have those things you wear on your wrists. You got your gym equipment. You got balloons, rubber ducks, again elastic bands, even bow and arrows, slinkies, the carriers for your bike, and especially springs, which is going to be one of the key objects we look at for this lesson. So one of the things about springs and these elastic objects is they have ability to stretch and bounce back to the original position. If, however, you overstretch them, you can go beyond their elastic limit. And if you go beyond the elastic limit, then they will not bounce back. So this spring here is broken, so it's not behaving in the correct fashion. So when we look at all of these laws and the things we deal with for elastic objects, if we go beyond the elastic limit, those rules will break down and they won't behave as we expected. The main figure in this chapter is Robert Hooke, who was an Englishman who lived between 1635 and 1703. So he's credited with the formalization and the study of springs, and there's a law named after him which we'll look at the end of the lesson. We're going to do this classic experiment, which is Hooke's law, and it looks at the relationship between the force applied to a spring and the extension. So we can deal with many different things here. We have our masses down here, which is 50 grams. Over here we can show the resting position, so that's the place the spring will be in. We have then the unstretched position, so this is the natural length of the spring, so that's the more common term we'll use, natural length, so this is the length the spring should be in a normal situation. That's shown by the blue line. We'll have the resting position, so that'll be further down, and we can also show some different stats. I've adjusted gravity here, so I've made gravity equal to 10 rather than 9.8 because that's going to be useful in our experiment. Here we're dealing with masses, but we prefer to deal with forces. So if I have gravity at 10, we'll get an easier relationship. If it's 9.8, then the results will kind of break down a little bit and we'll have to do some rounding off, and it just works better this way. So I've made gravity 10, so it's a slight change from Earth, but not too much. As I hang my first mass on the spring, we can see it bouncing up and down, and that's going to be one of the key things we look at all the way through this chapter. Thankfully I can stop it, unlike in real life. So I can see that this spring has moved from its unstretched length down to its resting position, so that's its displacement. The first figure I should have put in was we have a force of 0 newtons applied. That gave us a displacement or an extra stretch of 0 meters. So that figure we can know with certainty. Now I've added 0.5 newtons, so 50 grams corresponds exactly to 0.5 newtons because gravity is 10, and we can see how far that's stretched. So this ruler is given in millimeters, so it is 10 millimeters here plus 2 extra lines, so that is 12 millimeters. There are 1,000 millimeters in a meter, so this is 0.012 of a meter. Next I'm going to put on an extra half newton, so an extra 50 grams. And again stop it from bouncing up and down, which we're going to call oscillating later on, and this is one line before 25, so that is 24 millimeters, so 0.024. That's my second measurement. I add another half a newton, so up to 150 grams. Stop it bouncing, and I can take the extension, the displacement from the natural length to the resting position, and that is here at 36 millimeters. So we got 0.036. And here we can begin to see the pattern of how much extra displacement every 0.5 newton gives us. We can then add another half a newton, so up to 200 grams, 2 newtons, and then we can see that this is at a displacement from its natural length of 0.048 meters. We have 2 results left in this scale that it allows us, so up to 250. Again, stop it oscillating. That brings me up to 60 millimeters, so 0.060, which will round off, and my final measurement is down to 30. Now again, this is the handy thing, this resting position just stays stationary. In the lab you would need to get it to stop. Here I'm just using the figure that they did. If I was in the lab I might take it level with the top of the mass or even the bottom of the mass, but if I'm consistent we'll get the same displacement all the way through. So this final one here is at 72 millimeters, so 0.072. So this is my data, and I then need to graph this data. So if I highlight this, I'm going to insert, and then I pick charts, and I'm going to get my XY scatter. So this plots my X and versus my y. So at the bottom I can see here I've got my different forces, and up at the side I've got my different displacements. I can click on this, right click, and then I can add a trend line, and then it's going to be a linear relationship, and then that's all fine. I'm starting at 0, but what I would like to do is I'd like to display the equation on the chart. So that is this done here. So just make this a little bit bigger so we can see it. Back to home and pop that up. So we can see here it is a straight line graph through the origin, which shows us that force is directly proportional to displacement. Here we have this constant 0.024, and that is to do with the spring. So if I come back here, I can adjust the spring strength. I had it quite small, I wanted it to fit on the screen, but we can make this larger. So that constant there that we've determined in our graph, that is the spring constant. So that's a unique property for every spring, and if we adjust this, we will be able to determine the different spring constant for each one. So we have the relationship here that we can see. It's a straight line graph. So force is directly proportional to displacement. To make them equal, we need to bring in Hooke's law. And what Hooke's law tells us, I'll type it out over here, is that our force is equal to minus Ks. So that is our formula. Now the minus is a bit of a confusing thing, but the minus just in this instance tells us direction. So the force that we have is equal to minus K by S, because as force goes one way, the displacement goes the other. So that's what the minus brings in. The K is the spring constant, so that's a unique value for every spring, and again it can be found by experiment in this simple way to do Hooke's law. One of the other things we can look at on the internet, which would be more difficult in classroom, is how this works in the other direction. So typically we add weight to stretch the spring, but we can also compress the string more. Here it's easier because we have newtons. This is our Hooke's law thing. I prefer the other one, though it's a bit of a nicer way to do it. So here we can adjust our spring constant. So again, as we look, we bring the spring constant down, the spring gets a bit skinnier, and as we bring it up, the spring constant gets faster. So that means it's going to be more difficult to stretch out our spring, and we would need more force to do that stretching. So if we take a look here, we can show the applied force, which is the force I'm going to apply, and we'll also show the displacement. So we have this here, we can see the amount of newtons goes up, and as the amount of newtons goes up, the displacement goes up. Because this spring has a very high spring constant, we didn't get very far. As you bring the spring constant down, the spring has less resistance, less force in the other direction, so we can pull the spring a lot further. We still have the same 100 newtons, but now we've got much bigger displacement. And again, as we bring this down, we can see that they're directly proportional. So again, I'll start off at 0. So at 0 newtons, I have 0 displacement. Then if I bring this up to 10, we have 10 gives me 100. Double that up to 20, 200. Further on to 30, 300. So we can see that is a very predictable thing that shows us that displacement is directly proportional to force. Force is directly proportional to displacement. They are in the same direction, despite what I said before. I think I said it the wrong way, but force and displacement both go in the same direction. What goes in the other direction is the spring force. So the spring force, as you can see, is equal and opposite. So that's back to Newton's laws. So this is the other direction. So again, if we look at our formula here for Newton's law, F is equal to minus Ks. The minus is showing the direction. So this spring constant goes in the opposite direction to the applied force. So that's where the minus comes in. But it's equal in magnitude, equal in size. As we make that bigger, the other goes bigger, and it's in the opposite direction. So again, we can go the other way. We can compress the spring. So we can make the spring smaller. So this displacement, now we've gone back 100. So we've applied force in this direction. So again, we can just keep a track on this. We've applied a force, so that's our applied force of 100 newtons, and we've got 1 meter of displacement. It's easier to do it this way. So I come back to 0, so 0 on all directions. I'll bring this up to minus 10, so we've gone back 10, which gives me 100 in this direction. I can increase it to 20. 0.2, so you can see that they are directly proportional. back to 3, then up to 40, 0.4, 50, we'll predict 0.5, then we'll predict 0.6, 70 at 0.7, and so on. So we can have this easy relationship, and this was first formulated and proved out by Hooke, so it's known as Hooke's law. So again, key thing is these are going to be equal and opposite. The three things are the applied force, the resultant displacement, and the spring constant. So all of those things are important, and all of those things need to be known. We can mess around with these things and we can change lots of different values. So again, if I go back here, so we have a certain displacement for this here. So we have this applied force and we have this spring strength. If I make the spring strength larger, what's going to happen? We get less extension. And we get less extension because the spring is more difficult to move. So we are increasing the spring constant. If I make it maximum, I'm going to have the smallest one we can. If I then switch gravity, so if I make gravity to be regular Earth, slight difference because I had adjusted the gravity. If we make it the moon, much less gravity on the moon, so we have less weight. So this 300 grams gives us less weight because weight is equal to mass by gravity. If I bring it to Jupiter, we have much more gravity on Jupiter, so this 300 grams is a bigger weight. So it is easier in the lab to work in newtons, but here we're in grams, and it does again make it interesting. So these simulations are very good. They let us see all the different things we need to see, and we can even adjust all of the conditions to give us more power. So this again is Hooke's law, and Hooke's law states that force is directly proportional to displacement. It gives us a straight line graph through the origin, and we end up with this formula here. So force is directly proportional to displacement, and then we bring in the spring constant as another factor to make them equal. So again, F is proportional to displacement, and then that's our relationship. That's F is proportional to S, and then to make them equal, we bring in the spring constant K, and because it goes in the opposite direction, we get a minus. So that's our study of Hooke's law.